In this video, we will look at the features and characteristics of the graphs of polynomial functions. To start off, here's our standard form for a polynomial function. It can fit this pattern when we have it in expanded form, all multiplied out, not in factored form. We want to recognize that our terms here are in a descending order. So n is our degree. If you imagine maybe this is like a 10th degree polynomial, we'd have x to the 10th, then a term with x to the 9th, 10 minus 1, then a term with x to the 8th, 10 minus 2, and so on all the way down until a term with just x to the first, regular x, and lastly with a constant. The a part, that stands for the coefficients. The n, the subscript down here, that's just our label so that we know which coefficient matches up with which term. So a sub n is the coefficient on x to the n. A sub n minus 1 is the coefficient on x to the power of n minus 1, and so on all the way down. A sub 1, coefficient of x with an exponent of 1, and a sub 0 is the constant. And you could even say that we could put an x to the power of 0 on this last term to even show the pattern continues all the way, and we know anything to the power of 0 equals 1. That's why we don't see it the way I've written it here. Some details about the polynomials we'll work with. All the coefficients are real numbers, and in order for it to actually be a polynomial, all the exponents are whole numbers. So no negative exponents, no fractional exponents. That would make us not have a polynomial function, some other type of function. Two quantities that we care a lot about with polynomial functions are the degree n and the leading coefficient a sub n. As we begin to look at graphs, we will pay attention to how the graphs look compared to the degree of the polynomial and the leading coefficient. And specifically, we're really going to care about the sign of the leading coefficient. Is it positive or is it negative? Now let's look at a few examples of polynomial graphs, or graphs of polynomial functions. As we go through a few, I want you to pay attention to just the overall shape of the graph, as well as what we could see about the domain of the graph, what possible x values we see. Here's f of x equals x squared minus 3x minus 2, a degree 2 polynomial. Here's a degree 3 polynomial, degree 4. Here's a degree 5 polynomial, interesting one. Here's x to the 8th minus x to the 7th minus x to the 6th minus x to the 5th minus 3x to the 4th plus 3x to the 3rd plus 2x squared plus 6. One thing you may have noticed is that as the degree increased, the graphs had more action to them. The quadratic, the degree 2 that we're used to, we know it's always a smooth parabola, and as the degree increased with these examples, we saw more twists and turns in the graph. What did you notice about the domain? The ends of each of these graphs would shoot up, but the domain is all real numbers. But let's go with that observation about what happens on the two sides of the graph. We would see them on the ends either skyrocket upward or downward. In some cases it was both up, and in other cases one side was down and the other side was up. But one thing that we definitely want to say about polynomial graphs is that they are continuous and smooth. The continuous part means that as we move from left